Okay, well, let's get started. So last time we did the time-dependent heat equation on the line, and today we're going to do something. It's almost the same, exactly the same process actually. So we're going to look at the steady state heat equation on the upper half plane. Okay, so the problem is going to be this one, that we want the Poisson to be 0. Right, we want the, and remember the Laplacian is going to be second partial with respect to x, second partial with respect to y of u is going to be 0 on the open upper half plane. So, right, so up here where y is bigger than 0. And we're going to have an initial condition on the boundary. So we want, on the boundary, u of x naught should be equal to some function that we specify. Okay, so this is the problem. Okay, and so we're going to do this exactly the same way we did the last one. We'll just take the Fourier transform of everything, and then find out that that u has to be a particular convolution of f with some kernel. Okay, so yeah, when I was going over it this morning, I thought maybe I should have just skipped it because it's exactly the same process. But in any case, so as before, we proceed formally, and we just take the Fourier transform of everything. Right? So take the Fourier transform in x. So take the Fourier transform in the first variable. And you see that, as usual, the derivative turns into multiplication by negative 2 pi I c. So we get 4 pi squared c squared u hat c out of the first term, and then the second one is not affected by the Fourier transform. We just pass the Fourier transform through. We get the second derivative with respect to y of u of c. There should be a y here. U of c y equals 0, and then the second condition turns into u hat c 0 is f hat c. Right, so we just transform it. Okay. Okay. So we're doing kind of the same procedure as before. Okay. So here again, we have an ordinary differential equation, and then we just just solving the ordinary differential equation tells us that this thing is going to look like some function of c times e to the negative 2 pi absolute value of cy plus some other function of c times e to the 2 pi absolute value of cy. Okay. And we assume that the second function is always 0, because if it's not, then what we have is a function that is that grows exponentially, right? And that would mean that wherever that function is non-zero, then the solution has infinite energy, right? So that doesn't make any sense. Okay. So okay, so we assume that this part is just gonna be 0. Okay. And then we, as before, right, as before, we use the initial condition. We see that when y is equal to 0, then f hat c must be a of c, right? So we know what a of c must be. We see that altogether that u hat, right, must be f hat c times e to the negative 2 pi epsilon value for cy. Okay. In other words, u must be some convolution with some kernel. Right? For each y, u must be the convolution of f against some kernel. Okay, where p hat y is e to the negative 2 pi epsilon value of c. Right. So that's where we get formally, and then we need to figure out, so what we claim that if we let p be 1 over pi y over x squared plus y squared, then is the desired kernel. Okay, and this thing has a name. It's called the Poisson kernel. Okay, so it's not really a proof. It's just a calculation. You say, okay, well, we need to take the inverse Fourier transform. We need to take the inverse Fourier transform of that guy, right? So P of y should be the inverse Fourier transform. Should be the inverse Fourier transform of that kernel, right? So e to the negative 2 pi cy. E to the 2 pi I cx dx. Right? So you just take the inverse Fourier transform of that thing, and we split it into two parts. So then consider the integral from 0 to infinity of e to the negative 2 pi cy e to the 2 pi I cx dx. This is just a calculus problem, right? This is integral from 0 to infinity of e to the 2 pi I x plus pi y c dx, right? Which is e to the 2 pi I x plus I y c, right, over 2 pi I x plus I y between 0 and infinity. Right, so it's just calculus. Right? We get 1 over 2 pi I x plus I y. And then for the other part, from negative infinity to 0 of the same thing, we get 1 over 2 pi I x minus I y. And then you combine them together and you get this. So it's not, that's it. Add together. So just one minor comment. You know, normally when we said we were talking about integrals from negative infinity to positive infinity, we said we go from negative n to n, right? But if you can show that each of these guys converges, then the symmetric one will also converge to the same thing. So Okay, so so our guess is right. So our guess u xy being f convolved with p sub y x is our guess. Oh, also I forgot to say over here that at the same time we see that the Fourier transform, right? This thing is the inverse Fourier transform of this, so its Fourier transform is going to be this, right? If we take Fourier transform of that, we're going to get e to the negative 2 pi c. Okay. Another comment is that you might say, hey, we're taking the Fourier transform and inverse Fourier transform of this thing, but this thing is not in Schwartz class, right? This is actually just moderate decay, right? But there was that comment in the book saying that as long as your function is of moderate decay and its Fourier transform is of moderate decay, then the theorems still hold. Okay, so it's all right. Okay, is this all right? Mm-hmm. Yeah, this is just calculation, right? Just said, go through formally, what is it gonna look like, and then let's just calculate, by calculus what the kernel is gonna look like. Okay, so pretty straightforward. Okay, so at this point, we notice that luckily for us, Py, this collection of kernels, is an approximation identity. It's an approximation identity. And as usual, we've got 3 parts to it, right? You have to show that the L1 norm is 1. Yeah, thank you. That the L1 norm is 1. That the integral is bounded, and that that the integral is 1. That the L1 norm is bounded, and that it has that concentration at the origin thing. Okay. So 1 and 2 you can do simultaneously, right? Because it's positive. So Py is positive. So can do 1 and 2 simultaneously, right? But the L1 norm of function is the same thing as the Fourier transform of 0, right? Right. When you take the Fourier transform of something at 0, well, you get the integral of the function, right? So and the Fourier transform at 0 is 1, so that's that. As for part 3. You want to see that it's got this concentration quality. It's right. So remember what you're trying to show, that given any delta, given any neighborhood of the origin, then outside of that neighborhood, the function goes to 0. The integral goes to 0 as y goes to 0. And we want to show that the integral of Py dx for x bigger than delta goes to 0 as y goes to 0. But that also turns out to be a calculus equation because the integral from delta to infinity of y over x squared plus y squared dx, if you work it out, just turns out to be pi over 2 minus the inverse tangent of delta over y. Okay. And then as y goes to 0, this goes to 0. Okay, so everything is working out in exactly the same way as before. Yeah, like I said, I feel kind of like maybe I should have just assigned this as reading. But I guess there's some parts that are a little bit different. So what we're going to do right now. Okay, so so let's, just as before, we're going to see that that this works, right? That we can create solutions in this way. So given f in the Schwartz class, let u of xy be defined as f convolved with the Poisson kernel for xy in the upper half plane. Then u is twice continuously differentiable in the upper half plane. The Laplacian is 0. 2, u recovers f uniformly as y goes to 0. 3, u converges to f in L2 as y goes to 0. And 4, maybe I put this here. So this converges to f uniformly as y goes to 0. 4, letting u of x0 be f of x, then u is continuous on the upper half plane, unclosed upper half plane, and vanishes at infinity. In the sense that the function goes to 0 as the absolute value of x plus y goes to infinity. Okay, so coming back here, right, we're saying that you can get solutions to the steady state problem by just by convolving with the Poisson kernel. Everything happens as before, basically. So showing that it showing that the Laplacian is equal to 0. You do exactly the same kind of trick. You pass the derivative through and see that it works out. This is true because it's a good kernel. This is true because of an application of Plancherel's theorem. Just like that. So the only thing that's different is showing that this thing vanishes at infinity. Okay. So right. yeah, so we're going to do this in two parts. Proof 4, showing that it vanishes at infinity. Okay, so the first part, first you observe that when you convolve f with the Poisson kernel, right, you're getting f you get f of x minus y. This is bad notation. F of x minus t, py of t dt. Right, which is going to be f of x minus t, 1 over pi y over y squared plus t squared dt. Right. That's but this thing is controlled by some constant over y, right? Because if you throw out the t, this term just gets bigger, right? You're dividing by something smaller, so this term gets bigger, right? So this term is just c over y, and you're taking c over y. You pull out the c over y, and you get just the integral of the function. So that's a constant, right? So this thing is controlled by c over y. Okay, so that's good, right? We're trying to show that this thing vanishes as x plus y goes to infinity, right? So, right. So we'll split it into two cases. We'll say, suppose first that absolute value of x is greater than y. Okay, absolute value of x is greater than y. Well, in that case, as this term goes to infinity, whoops, wrong way around. So, absolute value of x is less than y. Sorry, right. Yeah. Okay. Right. Then as this term goes to infinity, then y must go to infinity, right? And in that case, well, by this bound, the function goes to 0. Okay. So then we need to look at the other case. Okay. So when absolute value of x is greater than y, right? When we're heading like this to infinity, you say, well, we use the following estimate. So we use this estimate, that f convolve with py of x is controlled by c times 1 over 1 plus x squared plus y over x squared plus y squared. Right. Right. And in that case, this thing is controlled by when absolute value of x is greater than y. Well, this is controlled by 1 over 1 plus x squared plus absolute value of x over x squared plus y squared. But again, we throw out the y squared. Right. We throw out the y squared, and we get some sort of bigger thing here. right? So this is like 1 over x squared and 1 over x, right? And then as you know, as this goes to infinity, you know, x goes to infinity, and so we get 0 again. Okay. Right. So all we need to do is prove this estimate, and then we'll be done with that. Okay. So to get this estimate, we break the integral into 2 parts. So we've got this thing, f of x minus t, p sub y, t and t. And we break it into 2 parts. One where t is small, t is smaller than absolute value of x over 2, and where t is bigger than absolute value of x over 2. Okay, and we play exactly the same sort of trick, right? Where t is small, that means that x minus t is basically x, right? And we do the same thing we did last time, right? We say, well, you know, we can bound this thing by, you know, so for where t is smaller than this, then f of x minus t is bounded above by 1 over 1 plus x minus t squared. But again, that's basically 1 over 1 plus x squared. Okay, because of this. Okay, so that gives us that this first term, right? That gives us that this first term is controlled by the 1 over 1 plus x squared. So then getting the second term, for the second integral, t is bigger than absolute value of x over 2. So, so the Poisson kernel, you know, y over t squared plus y squared is smaller than y over some constant times y over x squared plus t squared. I'm sorry, x squared plus y squared. Right. And that's it. That's it. Okay. Okay. So that shows that that the solution vanishes at infinity. Okay, so you know it's kind of the same story as before, right? Like you know you figure out that formally that the solution must be the convolution with something, with some kernel, and then luckily it turns out that it's a good kernel, and that that convolution with that kernel actually does give you the solution. So just as before, we're going to show that that the solution must be unique. So next, uniqueness. Okay. So to get uniqueness, we're going to need the mean value property of harmonic functions. Okay, so here it is. let omega be an open set, and u be twice continuously differentiable. If u is harmonic, then given any closed disk, Br xy in omega. So any closed disk centered at some point xy of radius r in omega. Then for all r between 0 and capital R, we have that u of xy, the value at that center equals the average of the value around over the circle of radius r. Centered at that point. Okay, so this is pretty cool, right? So if you're harmonic, right, you're harmonic in some domain. There's some disk in the domain. Then the average value over the disk equals the value at the center, right? So the average value over every disk is going to be the value at the center. So, right, this can be used to show that that harmonic functions satisfy a kind of maximal principle, right? That the maximum value must occur on the boundary. Right? We'll do that right after this. Okay, so. The proof goes as follows. There are one proof. There are a lot of proofs of the mean value property. Stein does it as follows. He says, well, let define capital U of r theta as the value at the point r theta on the circle around that point. Okay, so, right. Okay, so then, if you take the Laplacian and then you change it into polar coordinates, this in polar coordinates says exactly that the second partial with respect to capital U, second partial with respect to theta plus r times the first partial of the product r times du dr equals 0. Okay. This is exactly the Laplacian in polar coordinates, just written in a kind of funny manner. Okay. Right. When you take the partial of this thing, you're going to get 1 times the second partial of this plus r times the first plus
r times the second partial plus 1 times the first partial.
Yes, thank you. Yeah, thanks. Yeah, which is which plus this is the Laplacian in polar coordinates.
Has it been scaled by like r squared or something?
Yeah, it's just multiplied through by r squared. Yeah. Okay. Okay. So now let f of r be the integral. Let f of r be the integral, or the average, sorry, of capital U are beta contingent. So we're hoping to see that, right? This is this thing on the right hand side, and we're hoping to see that that f is constant. That f is constant. Okay, so differentiating. Right, we, I mean, using right, so using the above fact, we see that R partial with respect to R of R df dr is the same thing as 1 over 2 pi from 0 to pi of negative du d theta squared R. Okay, so just, you know, right, because when we do this to f, that's the same thing as, you know, by this we're gonna just get negative at the second partial with respect to theta. Okay, so but du d theta is periodic. So this term is 0. Right? So the right hand side is 0. Okay. What does that give you? That tells you that that this term R df dr is constant. Right? R df dr is constant. That constant must be 0 because when you take R 0, the product is 0, right? This product is constant. Well, take R to be 0. That tells you that the constant is 0. But that tells you that df dr is 0, which means that f is constant. Right, and f when R equals, right, it's going to be constant equal to u of xy because that's the value of f at 0. So since f at times 0 is just u of xy, right? We're just averaging the value u of xy, which is u of xy. We get that f is constantly equal to u of xy. Okay, so that's kind of a cute proof of the mean value property. Is that okay?
And
yes.
the property is saying that it's the average value taken of the circle at any r, not over the disk.
Yeah.
Okay.
Yeah. So just the average over any circle of radius little r between 0 and big R.
Okay.
Okay. So now let's use that to prove uniqueness.
We didn't use any of the previous results about you know, the Poisson kernel being a good kernel actually to prove this, right?
Not this part. That was for the previous three facts, right? Just saying that the Poisson kernel converges uniformly. The Poisson integral converges uniformly. And stuff like that.
So we could have proven this a while ago.
That's true.
Yeah.
That's true. Yeah, this is just a fact about harmonic functions. Yeah. Yeah. So, and we're just introducing it now to prove the uniqueness part. Yeah. Okay. So, theorem. This is uniqueness. So let U be a solution to let U be a harmonic function on the upper half plane. If U is continuous on the closed upper half plane, if U on the boundary is 0, and 3, U vanishes at infinity, then U must be the 0 function. So if you have two guys that agree on the boundary, then they must agree everywhere. Okay. So the proof goes like this. Say, okay, suppose that, so loss of generality, suppose that U is real valued, and that U is non-zero somewhere. Suppose it's non-zero somewhere. Okay. So there's some point where you're non-zero. So now take a semidisk dr plus. Okay. So it's going to be it's just going to be a disk, but chopped off in the upper half plane. Okay. Disk of radius r. Okay. With r so large that the function is smaller than this value. So that on the semidisk, on the complement of that semidisk, U is small. It's smaller than that. Okay. So okay. Yeah, actually, this semi, I've drawn it looking like it's centered at x naught, y naught, but actually, we're just taking it centered at the origin. Sorry. Okay. So. Okay. So since U is continuous. Since U is continuous, it's going to be, it attains a maximum on the, at some point, at some x1, y1 in that disk, right? So there's some place where you attain a max. Okay. Now we use the mean value property, right? The mean value property says that the mean value property says that whatever disk you take, the average value over the disk equals the value at the center, right? But this is the maximum value, right? This being the maximum value means that it has to attain that maximum value over the entire disk, right? At every point on the disk, it has to attain that maximum value, because otherwise, you're not going to. The average is not going to be this maximum value, right? So by the mean value property, you know that for any disk, centered x1, y1, the average value is going to be n. But that means that u of xy is m on at each point of the disk. Right, since n is the max. Right. It's going to attain that value at each point of the disk. Well, continue that. When you expand that to take the radius y1, and that tells you that that some point on the boundary that at u of x0, x1 comma 0 has the value m there, but u is supposed to be 0 on the boundary, so that's a contradiction. Okay. So that's how you see uniqueness, and you see that that the main value property. So remark that we have this maximum principle. We've basically just given the proof of the maximum principle that if a non-constant function is continuous on a closure of a bounded domain, and harmonic on the interior, then the max must occur on the boundary. Right. Because if it occurred on the interior, you can play this game and then push it out to the boundary. Okay, that's it.